In this video, we're going to look at another example of work integrals. So we have a heavy cable 10 meters long that weighs 2 kilograms per meter. That's a linear density, 2 kilograms per meter. Hangs over the edge of a building 12 meters high. How much work in joules is required to pull the entire 10-meter cable to the top of the building? So we have gravity as 9.8 meter per second squared, and we have the density of the cable, which is 2 kilograms per meter, the linear density. So our strategy will be to find the mass of a small segment of the 10-meter cable and find the force acting on this small piece of cable and find the work required to lift this cable piece, this segment of the cable, to the top. Then the integral adds it all up. All right, so here we have a drawing. We have the cable. You can see it's a 10-meter cable, and notice that when this cable is y units from the ground level, it has to be lifted. This segment of the cable has to be lifted 10 minus y units. That's very important. We have the cable linear density, mass per unit length as 2 kilograms per meter. We have gravity to be 9.8. So a piece of cable with length dy with linear density 2 kilograms per meter has a mass of 2 kilograms per meter times the length dy meters. So essentially we get 2 dy. This is the mass of a small segment, this segment here, a small segment of the cable. So differential mass is equal to 2 times dy. This is the mass of a small piece of cable. All right, so differential mass is equal to 2 dy, mass of a small piece of cable. Let's find the force of gravity acting on this small piece of cable. Differential force is equal to 2 times 9.8 times dy. This is the force acting on this cable piece. Now let's find the work required to lift this small piece of cable 10 minus y meters to the top of the building. So that's 10 minus y times df. And if we simplify this, we get dw is equal to 10 minus y. Now plug in differential force, which is 2 times 9.8 dy. The most important part is this part, 10 minus y. And if you look at the diagram, you can see why that is. This small piece at height y has to be lifted 10 minus y units to reach the top. We can also test this out. Imagine that the small piece is at y equals 0, at ground level. How many meters does that small piece have to be raised to reach the top? Well, that's 10 minus y, 10 minus 0. So 10 minus y equals 10 minus 0, 10 meters, and that agrees with our intuition. What about a piece of cable that's at the top? Well, that's going to be 10 minus y. That's 10 minus 10, substituting y equals 10. I'm going to 0 meter, and that also agrees with our intuition. If a piece of cable is at the top, it doesn't have to be raised anywhere. All right, so we have dw is 2 times 9.8. So this is the rho, the density, and this part is gravity, and this part, of course, 10 minus y is the distance that each segment of the cable has to travel to reach the top. So the key concept is work is equal to force times distance. So why do we need an integral to solve this? The reason is each piece of the 10-meter cable is lifted different vertical distances to reach the top. Each piece of the 10-meter cable has to travel 10 minus y meters, which is a variable distance. This is a variable distance. And for that reason, we need an integral to solve this. So the work integral will be integral from 0 to 10 dw. All right, so let's set up a definite integral and find the work needed, the work required to lift this cable to the top. So dw is equal to 2 times 9.8. This setup is very important, and you don't want to leave anything behind. So this part is the linear density of the cable, 2 kilograms per meter. That means every meter of the cable has the mass of 2 kilograms. This part is 9.8. This is gravity on Earth. 10 minus y is, of course, the distance that each segment of the cable has to travel to reach the top. So the work done is going to be the integral from y equals 0 to y equals 10 dw This is equal to integral from 0 to 10, 2 times 9.8 times 10 minus y dy. 2 times 9.8, this is just a constant passes through the integral, so the work is equal to 2 times 9.8 integral from 0 to 10, 10 minus y dy. This is a very easy integral to do. So we get work is equal to 2 times 9.8, put into a calculator, that's 19.6. Integrating 10 minus y piece by piece. What's the integral of 10? That's just 10y, reversing the power rule. And what's the integral of y? Well, that's just going to be y squared divided by 2, add 1 to the exponent, divide by the same. Now apply the fundamental theorem of calculus, integrate from 0 to 10. Evaluate, I should say, from 0 to 10. So we get 19.6, work is equal to 19.6 times. Plug the upper limit in, we get 100, 10 times 10, that's 100, minus 10 squared is 100. Divide by 2, minus, put the lower limit in, 0 minus 0, and close off the brackets. So the work done is 19.6 times 100 minus 100 over 2, that's 100 minus 50, that's 50. Put that into a calculator, we get 980 joules. That means 980 joules of work is done to lift the cable to the top. Let's show that on a diagram. 980 joules of work is required to lift this cable to the top. The reason we need an integral intuitively is because in the beginning you're lifting the entire length of that chain, the entire 10 meters of this cable. But as you lift more and more of it, less of the cable is hanging over the edge of the building, and it gets easier and easier to lift up the rest. So that's the reason that each segment of the cable travels a different distance, and for that reason we needed to integrate and set up a work integral. All right, thanks.